Welcome to Organic Chemistry. Today we are going to explore the reactions of alkynes. Imagine you have a thick, heavy-duty rubber band stretched out as far as it can go. It is holding a lot of tension, and the moment you let go, it snaps back into a more relaxed state. In organic chemistry, a carbon-carbon triple bond is very much like that stretched rubber band. It contains a massive amount of stored chemical energy. Let us dive in and see how we can harness this energy. Now that we understand the rubber band analogy, let us look at the chemical structure. Alkynes are unsaturated hydrocarbons with at least one carbon-carbon triple bond. This bond consists of one strong sigma bond and two weaker pi bonds. Because pi bonds are formed by sideways overlapping electron clouds, they are much easier to break. This makes alkynes eager to react. Interestingly, because the sp hybridized carbons in a triple bond pull electrons very close to themselves, they are highly electronegative. This makes them surprisingly good at attracting chemical species that have extra electrons to share, known as nucleophiles. Building on this understanding of their structure, let us examine their acid-base behavior. Terminal alkynes, which have the triple bond at the very end of the carbon chain, possess a unique property. Their terminal hydrogen is unusually acidic. When we introduce a very strong base, it acts like a chemical thief, stealing this hydrogen atom. This leaves behind a carbon atom holding a negative charge, called an acetylide ion. The rounder sp orbital holds this negative charge close to the nucleus, stabilizing it beautifully without the molecule falling apart. This concept of acidity leads us directly to our first key chemical equation. Here we see a generic terminal alkyne reacting with sodium amide. The R represents any carbon chain. Sodium amide is our strong base. It strips the hydrogen away, forming ammonia gas and leaving behind the acetylide ion. Notice the negative charge on the carbon? If we increase the concentration of the base, the rate at which the terminal hydrogen is removed increases, rapidly producing more acetylide ions. This negatively charged ion is incredibly useful, as it is now primed to attack other molecules. Now that we have this negatively charged acetylide ion, what do we do with it? We use it to build bigger molecules in a process called alkylation. Because the acetylide ion is negatively charged, it acts as a powerful nucleophile, meaning it aggressively seeks out positive charges. We can introduce an alkyl halide, which is a carbon chain attached to a halogen. The acetylide ion attacks the carbon in the alkyl halide, kicking out the halogen. Think of this like snapping two Lego pieces together to build a longer carbon chain. This building process is perfectly captured in our alkylation formula. The acetylide ion reacts with R'(X), where R' is a new carbon chain, and X is a halogen like bromine or iodine. The nucleophilic carbon attacks R', and the halogen X is expelled as a negative ion. This forms a brand new carbon-carbon bond, resulting in a larger internal alkyne. If we use an alkyl halide with a longer carbon chain, the resulting alkyne will physically be much larger and heavier, completely changing its physical properties like boiling point. Before we move on, let us see this with a concrete example. Suppose you're given ethyne, a simple 2-carbon alkyne, and you need to synthesize 1-butyne, a 4-carbon alkyne. We need to add 2 carbons. First, we must turn our starting ethyne into a strong nucleophile. We do this by reacting it with the strong base sodium amide. The base strips away one terminal hydrogen, leaving us with sodium acetylide. This negatively charged 2-carbon piece is now primed and ready to attack our next molecule. Continuing with our synthesis, we now have our nucleophile ready. Next, we introduce bromoethane, which provides the exact 2 extra carbons we need to reach our target length of 4 carbons. The negatively charged acetylide attacks the carbon attached to the bromine. This collision forces the bromine atom to detach and leave entirely. The two pieces snap together, giving us a final product, 1-butyne. Physically, we have transformed a light gas, ethine, into a heavier hydrocarbon simply by snapping carbon chains together. Now that we have mastered alkylation, let us explore another major reaction, hydration. Hydration simply means adding water across the triple bond. However, this reaction is too slow to happen on its own. It requires a catalyst, typically mercury ions and an acid source. The water molecule splits into a hydrogen atom and a hydroxyl group, which add to the two carbons of the triple bond. This addition breaks one of the pi bonds and forms an intermediate molecule called an enol, which is an alkene with an alcohol group attached. This brings us to the chemical equation for hydration. We start with our alkyne and add water, using mercury 2+ and H+ as catalysts. The water splits, adding an OH group to one carbon and an H to the other, forming the enol. Conceptually, the catalysts lower the energy barrier, allowing the stubborn triple bond to open up. If we were to remove the catalysts, the reaction rate would drop to almost zero. But remember, this enol intermediate is highly unstable and will not stay in this form for long. Because the enol we just formed is so unstable, it immediately undergoes a fascinating process called tautomerization. Tautomerization is a rapid chemical rearrangement. Imagine a person standing on one leg, representing the unstable enol, who quickly puts both feet on the ground to balance themselves. In the molecule, a hydrogen atom moves from the oxygen to the neighboring carbon, and the double bond shifts from the carbons to the carbon-oxygen bond. This internal shifting converts the unstable enol into a highly stable ketone, which is almost always the final result of hydrating an alkyne. Let us look at the exact mathematical representation of this rearrangement. The equation shows the enol in equilibrium with the ketone. The double bond between the two carbons shifts to form a carbon-oxygen double bond, while the hydrogen from the OH group migrates to the end carbon. Conceptually, this is driven by the molecule seeking a lower, more comfortable energy state. If we observe this in a lab, the equilibrium heavily favors the right side. Increasing the amount of enol will just result in an immediate, rapid conversion into more of the stable ketone. Now that we have the formulas, let us apply them to a real problem. Suppose you are given propyne, a 3-carbon alkyne, and you mix it with water, sulfuric acid, and mercury sulfate. What is the final product? First, we know water will add across the triple bond. This follows Markovnikov's rule, meaning the hydrogen attaches to the carbon that already has more hydrogens. The OH group attaches to the middle carbon. This specific placement forms our unstable intermediate, 1-propene-2-ol, which is an enol. Continuing with our propyne reaction, we cannot stop at the enol because it is highly unstable. Immediately, it undergoes tautomerization. The hydrogen on the oxygen shifts over to the end carbon, turning the CH2 group into a CH3 group. Simultaneously, the carbon-carbon double bond shifts to become a strong carbon-oxygen double bond. This gives us our final answer, acetone. Physically, we have taken a highly reactive alkyne gas and transformed it into a stable liquid solvent, commonly used as nail polish remover. The reaction heavily favors this stable ketone form. To truly cement this idea, let us look at a visual summary of the hydration process we just solved. On the far left, you see the linear triple-bonded propyne molecule. Following the first reaction arrow, which includes our mercury and acid catalysts, we move to the middle structure. This is the temporary enol, shown in brackets to indicate its instability. Finally, the equilibrium arrow leads us to the right, showing the stable, double-bonded ketone, acetone. Notice how the atoms physically rearrange themselves during the tautomerization step to achieve a lower energy state? Before we conclude, You might wonder why these specific reactions matter outside the classroom. Alkynes are the ultimate chemical building blocks. Because the triple bond is so reactive, and because terminal alkynes can easily be turned into carbon chain building nucleophiles, they are absolutely essential in the pharmaceutical and plastics industries. For example, the active ingredients in many oral contraceptives are synthesized using the exact alkyne alkylation process we learned today to build their complex steroid structures. Without this chemistry, manufacturing these life saving drugs would be incredibly difficult and expensive. We have covered a lot of ground today, so let us summarize the most important ideas. First, alkynes are highly reactive molecules driven by the energy stored in their carbon-carbon triple bonds. Second, they undergo addition reactions like hydration, which break the pi bonds and ultimately form stable products like ketones through tautomerization. Finally, their terminal hydrogens are acidic, allowing strong bases to create powerful nucleophiles used to build longer carbon chains. Mastering these reactions gives you the fundamental tools to construct almost any organic molecule. Great job today.